Welcome to Rory Academy YouTube channel 2.0. Our new and improved channel is dedicated to showing you how things are put together, from concept to prototype. Here, we break down the art of designing, assembling, and testing real engineering systems, helping you understand the science and creativity behind innovation in power electronic-centric systems and devices in our 5-minute video clips. Before we go into today's lesson, let's take a quick look at an incredible diagnostic tool that every EV engineer or enthusiast should know about, the Autel MaxiZis Ultra EV. This is a next-generation full-system diagnostic scanner designed for electric, hybrid, gas, and diesel vehicles. What makes the Ultra EV stand out is its ability to perform a comprehensive analysis of electric and hybrid vehicles, including advanced topology mapping and battery pack analysis. You can perform diagnostics via an OBD connection or directly through the included specialty cables and jumpers, perfect for in-depth testing of high-voltage battery systems. The 12.9-inch touchscreen tablet provides a clear, detailed view of your diagnostic results. Now, let's see how this powerful diagnostic tool is set up and operated in real time.
Our EV-related diagnostic software on our Ultra series of tablets. New Energy, green button. And this is going to be the button that you'd want to see. Quite a robust selection of vehicles that are EV software pack test. And you'll notice that once we connect to the car, it's going to give us a little bit of disclaimers, some high voltage safety related information. I'm going to go ahead and communicate with the vehicle. I'm going to select the blue button here that says battery pack information, and it's going to pull up a whole host of diagnostic information to help you repair that vehicle. So the first screen that comes up is our module status. You can see some overall general information at the top of the screen of different information about the battery pack, the state of charge, the state of health, the total voltage. But then at the bottom, we're going to see the infrastructure of how many modules this particular battery pack has. In every module, there are several cells. So if I have the button at the top of the screen that's called cell status. Cell status allows me to look at the individual cells of all the modules all at once. So I have a couple ways I can view it. If I hit the 4 little squares, it allows me to see all the actual voltages. The ones in red and blue represent the highest cell voltage and the lowest cell voltage from the battery pack, and it tries to balance them to be equal. At the top of the screen also, we have the battery pack info button. This gives me all the information that I need about this battery pack. Very helpful for, at the top of the screen, is the other live data button. So here is all the other data that the BMS, the battery management system, is allowing us to see all at once. And just like every other part of your diagnostic.
Hey guys, if you're into EVs or work with electric cars, you need to check this out. The Autel MaxiZis Ultra EV Diagnostic Scanner is seriously one of the best tools out there for deep dive battery diagnostics and full system testing on electric and hybrid vehicles. It's fast, accurate, and super easy to use. Honestly, a total game changer if you're serious about understanding your EV inside and out. So if you want to grab yours, just click the link in the video description below and check it out. In this video, we're exposing the power electronics design choice that makes the Model 3 performance brutally efficient and insanely responsive silicon carbide modules versus discrete devices. Why Tesla should move away from traditional discrete SiC layouts. What do you gain and what do you lose when you go modular? And how do thermal performance, switching losses, packaging parasitics, and reliability decide who wins? I'll break down Tesla's inverter architecture, show you what's actually inside, and explain why this SiC decision matters not just for Tesla, but for the future of high-performance EVs. If you're an engineer, this will sharpen your design intuition. If you're an EV enthusiast, you'll finally understand what makes Tesla different. Let's open the inverter. Let's take a closer look at the front axle powertrain of the Tesla Model 3. What you're looking at here is a highly integrated system made up of 3 core elements: a permanent magnet synchronous motor, a single-speed reduction gearbox, and a high-efficiency power inverter. The inverter is the brain of the system. It converts the DC energy from the battery into precisely controlled three-phase AC, switching at tens of kilohertz using silicon carbide power devices to maximize efficiency and power density. That electrical energy feeds the permanent magnet motor, where electromagnetic torque is generated almost instantly, giving the Model 3 its sharp throttle response and strong acceleration. The gearbox then steps down the motor's high-speed rotation into usable wheel torque, delivering smooth and efficient power directly to the front wheels. What makes Tesla's approach unique is how tightly these elements are integrated. By minimizing electrical and mechanical losses, reducing parasitic inductance, and optimizing thermal paths, Tesla extracts more performance from less hardware. In this video, we're going to break down how the inverter design, especially the choice between SiC modules and discrete devices, influences efficiency, thermal behavior, and overall vehicle performance. Let's dive inside the inverter. The very first thing you see after disconnecting the inverter from the powertrain is the printed circuit board, and this is where Tesla's power electronics philosophy really comes into focus. This PCB is a masterclass in high-density power electronics. It acts as the nerve center of the inverter, integrating control logic, gate driving, and high-voltage sensing into a single, tightly optimized unit. There's even a quirky engineering Easter egg here. The board is famously cut into the rough silhouette of the United States, a subtle signature hidden inside one of the most advanced EV inverters on the road. More importantly, this board is mounted directly on top of the discrete SiC devices and the DC-link film capacitor. That physical proximity is not accidental. It drastically shortens the gate drive signal paths, which is absolutely critical when you're switching silicon carbide devices at very high speeds. Tesla combines logic control and power gate driving onto a single, highly complex 6-layer PCB, reducing parasitics, improving switching behavior, and pushing efficiency and power density even further. This is not just clever packaging, it's performance-driven engineering. At the heart of the control circuit sits the microcontroller, the brain of the inverter. Tesla utilizes a Texas Instruments TMS 320F28377D, part of the C2000 series, a processor family specifically designed for real-time motor control. This device features a dual-core architecture running at 200 MHz, giving it the computational headroom needed to execute complex field-oriented control algorithms with precise timing and extremely low latency. Surrounding the controller are 6 dedicated gate driver ICs, STMicroelectronics STGAP1AS isolated gate drivers. Each gate driver controls 4 silicon carbide FETs, bringing the total to 24 SiC devices in the inverter power stage. These gate drivers provide galvanic isolation between the low-voltage control electronics and the high-voltage power section, a critical requirement for safety, noise immunity, and reliable high-speed switching. The result is a control and drive system capable of switching SiC devices cleanly, efficiently, and repeatably, even under the extreme electrical and thermal stress of high-performance EV operation. This is where software, silicon, and power truly come together. Once the control PCB is removed, we're left with the heart of the power stage, the discrete silicon carbide MOSFETs. In total, there are more than 24 individual SiC devices, each one silver-sintered directly onto the copper busbar through the drain and source terminals. This sintered attachment provides extremely low electrical resistance, excellent thermal conductivity, and long-term mechanical reliability, far beyond what traditional solder can achieve. The gate and Kelvin source terminals of each device are then soldered directly to the PCB, creating tightly controlled gate loops and clean switching behavior, which is absolutely critical at silicon carbide switching speeds. Positioned right alongside the power devices is the DC-link capacitor bank. Placing the capacitors this close to the MOSFETs dramatically reduces loop inductance, suppresses voltage overshoot, and stabilizes the DC bus during fast current transients. This layout is a textbook example of low inductance, high-performance power electronics packaging, and it highlights exactly why Tesla's discrete SiC approach delivers such high efficiency and power density. This is packaging as a performance enabler. Thermal management is one of the most critical and least visible parts of the Tesla Model 3 inverter design. Silicon carbide devices can switch incredibly fast and handle high junction temperatures, but performance is always limited by how efficiently you can remove heat. And this is where Tesla's inverter structure really stands out. The discrete SiC MOSFETs are silver-sintered directly onto a copper busbar, creating an exceptionally low thermal resistance path from the semiconductor junction into the cooling structure. This direct metal-to-metal interface allows heat to spread quickly and uniformly. Beneath the power devices sits a liquid-cooled cold plate, integrated into the inverter housing. Coolant flows directly under the highest heat flux regions, pulling energy away from the devices before temperatures can spike during hard acceleration or regenerative braking. By mounting the DC-link capacitors and power devices in close proximity, Tesla also minimizes parasitic inductance, reducing switching losses that would otherwise turn into unwanted heat. What's especially clever is how electrical, thermal, and mechanical design are treated as one system. Short current paths reduce losses, efficient cooling keeps junction temperature stable, and that thermal stability directly improves reliability and lifetime. Let's take a deep dive into the automotive-grade silicon carbide power MOSFET used in the current Tesla Model 3 inverter. Tesla selected STMicroelectronics' third-generation silicon carbide MOSFET technology, one of the most advanced discrete SiC platforms available for high-performance automotive applications. These devices are engineered to deliver exceptionally low on-state resistance across the entire operating temperature range, a key advantage in electric vehicles where thermal conditions can change rapidly. Combined with low parasitic capacitances and the ability to operate at very high switching speeds, this technology significantly improves inverter performance, enabling higher switching frequencies, greater energy efficiency, and reduced system losses. The benefits go beyond efficiency. Faster switching and lower losses allow for smaller passive components, which directly translates into reduced system size and lower overall weight, critical factors in EV powertrain design. The specific device used here is STMicroelectronics part number SCTHS300N75G3AG, rated for a drain source voltage of 750 volts and a continuous drain current of 300 amperes. This combination of voltage capability, current density, and switching performance makes it an ideal building block for a high-power, high-efficiency automotive inverter. This is silicon carbide doing exactly what it was designed to do, push performance beyond the limits of silicon. With 24 discrete silicon carbide MOSFET devices used for the Tesla Model 3 inverter, 4 paralleled silicon carbide MOSFET devices connected per switching position. Therefore, the established failure modes affecting SCTHS300N75G3AG class SiC MOSFETs when connected in parallel in high-power automotive inverters, focusing on physical connection and parallel interaction effects are 1. Device and parallel configuration. SCTHS300N75G3AG is a 750 volts, 300 amperes automotive-grade SiC MOSFET, AEC-Q101 qualified, intended for traction inverter use and capable of high-speed switching and low on-state resistance. In Model 3 traction inverters, multiple SiC MOSFET die are paralleled per switch position to meet current rating and reduce individual junction stress. Industry teardown analyses show 8 die per leg to limit junction temperature under load. 2. Current sharing and unbalanced stress. In parallel, small variations in device parameters, e.g., threshold voltage, on resistance, breakdown lead to uneven current distribution. Devices with slightly lower breakdown voltage or on-state resistance will hog current, experience higher self-heating, and degrade faster, especially under avalanche or fault conditions. 3. Parallel avalanche capability degradation. During inductive switching or transient overvoltage events, energy must be dissipated by MOSFETs. Slight differences in breakdown characteristics among parallel MOSFETs can cause some chips to enter avalanche earlier and carry most of the avalanche current. This leads to thermal imbalance, accelerating degradation or failure in the weakest device first. By replacing the parallel discrete SCTHS 300N75G3AG devices with the CAB760M12HM3 silicon carbide half-bridge module, Tesla effectively eliminates these parallel connection failure mechanisms. By adopting the CAB760M12HM3 half-bridge module, Tesla achieves fewer switching elements and interconnections, lower part count and assembly complexity, improved robustness under high torque transients and regenerative braking, increased inverter lifetime under aggressive automotive duty cycles. Most importantly, the dominant failure mode associated with parallel discrete SiC MOSFETs is fundamentally removed, resulting in a more reliable, manufacturable, and scalable traction inverter architecture. Thank you so much for watching today's video and exploring how the reliability of the Tesla Model S inverter can be significantly improved by using silicon carbide power modules instead of traditional discrete devices. Remember, here at Rory Academy YouTube channel 2.0 you watch, learn, and understand how to prototype. See you in the next video. If you found this video insightful, don't forget to like, subscribe, turn on notifications, comment, and share, so you never miss our next deep dive into the world of technology and innovation.